Alrighty, so today is the final exam review for the class. The final exam is set for this class to be held on Thursday, which would be May 5th. So this Thursday is the final exam. We will be holding it online. So it'll be done just like the previous tests were done. I'll post it in the morning of Thursday. You download it, work out all the problems, and then you'll have till 11:59 p.m. to submit the finished final exam. Even though it's online, just like the previous test, that doesn't mean I'll make it any longer than the test would have been had it been done in class. So just as with all final exams at Dillard, it's a 2-hour exam, which means it's twice as long as a regular test. And so you can expect about twice as many problems to be on the final as there were on the previous tests. So probably somewhere around 12 to 15 questions. The format and all of that will be just like the previous tests. So you're used to what the tests look like by now. You know the style of questions I ask. It'll be the same type of thing. So nothing new there. The only difference being this is a cumulative exam. So it covers all of the material over the semester rather than just one of the topics. So let's see, what were the topics we've gone over this semester? Basically, the way I see it, we have kind of 3 overarching subject matters. The first was thermodynamics. So that was the first topic we did. Now, of course, I'm not including the mathematical review we had at the beginning of the semester. That was just to review the math that was going to be used during the course of the semester. There's not going to be any particular specific math-only questions. This is a physics course, and so all the questions are on the physics. So where everything starts is with thermodynamics. The first big topic under thermodynamics we had was calorimetry. Calorimetry, those were the types of questions where you have something like you have a hot cup of coffee and you want to cool it down to 80 degrees. How much milk should you add? Or you have an ice chest filled with a whole bunch of different things, all at different temperatures, and you let it sit for a while. What will be the final temperature of the ice chest? Those types of questions. And so we had kind of 2 big equations there. Q equals Cm delta T, which was the equation you would use if the object changes temperature, how much energy is required to change the temperature of an object. And the other, Q equals M times L, latent heat version, was for those cases where the object changes phase. So if you have ice in the system, you can heat up the ice, that's Cm delta T, and the ice can melt. The melting part is M times L. And a combination of those put together for the system is what you would use to do a calorimetry style of problem. From there, we talked about heat conduction, or heat transfer through conduction. These were the types of questions where you have a wall of a certain thickness made of a particular material, so you know its conductivity. The outside of the wall is at 100 degrees, the inside is at 50 degrees, and you want to know what is the heat transfer rate, or how much energy is transferred through the wall per second. And that was Q over T. That's the heat transfer rate, is K A delta T over L. where K, of course, conductivity, A, that's the size of the wall, the area of the wall, delta T, that's the difference of temperature from one side of the wall to the other, and then L was how thick is your wall. And then, of course, we also had some questions where maybe you had two different materials put together and you want to know how much heat flows through the system. And for that, you'd use this equation, but you'd use it in the form Q over T for the first material is equal to Q over T for the second material. That is, if you have two materials, wall and insulation, and you want to send heat through that system, then you know that the heat transfer rate through the wall part must be equal to the heat transfer rate through the insulation part, because the heat has to go through everything. So you would say Ka delta T over L for the wall is equal to Ka delta T over L for the insulation, and so forth. And then the last part of thermodynamics we talked about was radiation. Heat transfer by radiation. And this had the kind of question again, what's the heat transfer rate? How much energy is radiated from an object of a certain temperature, or the power radiated? That's given by Q over T is sigma epsilon A T to the fourth. Here, sigma, that was the constant, the Stefan Boltzmann constant. That's, and all constants that you have to know would be given on the test, so you don't have to memorize the number. That was just some number that we had to include in. Epsilon, emissivity, that is how well does the object radiate energy? Certain materials radiate very well, certain materials don't. And so you may have an object that radiates at 20%, or you could have a perfect radiator. That's what the epsilon tells you. A, that's the surface area of the object. Of course, a bigger object has more space for the energy to radiate away from than a smaller object does. So a bigger object can radiate better than a smaller object. And then, of course, T to the fourth, that's the temperature. Now for this is the first time in thermodynamics that we cannot use Celsius. Remember, in all of physics, we're supposed to be using Kelvin units for our, what would I say, temperature. Temperature unit should be Kelvin. However, if you have delta T, we found out that there was a trick. We could use the fact that a change in temperature of Kelvin is the same as change in temperature of Celsius. And so if we ever see delta T, we could use Celsius if we'd like. Here, there is no delta T, so we have to use Kelvin. So before you use this equation, you have to convert the temperature to Kelvin. Then you could use the equation. And of course, we also saw particular examples where maybe the object is placed in an environment which is at some other temperature. You know, you put a hot metal sphere into a refrigerator. And so we just modified this equation a little bit to say Q over T is sigma epsilon A. And then instead of just T to the fourth, we have the temperature of the object to the fourth power minus the temperature of the environment to the fourth power. Okay, so if I don't tell you about the environment, then you use the first equation. If I do tell you about the environment, you use the second one. And that's thermodynamics. Those were the three subtopics underneath thermodynamics. And that's what the first exam was on. From there, the next exam covered fluids. And so with fluids, we had a number of subtopics, the first of which being Bernoulli. And with Bernoulli, these questions were the types where you have some kind of a pipe system with a fluid flowing through the pipe. And the pipe is allowed to go up or go down in height. It's allowed to expand or contract, change size. And you're trying to figure out, how does the pressure of the fluid change because of the changes in the pipe? And the equation was fairly straightforward. It said P1 plus 1/2 rho V1 squared plus rho G H1. That's the total kind of pressure in the system is constant. So it's equal to P2 plus 1/2 rho V2 squared plus rho GH2. So if you have a pipe, the pipe goes up to the second floor and then constricts to some new size, and you want to find out, how does the pressure change? This is the type of equation you would use. And then, of course, we needed a secondary equation to help us use this equation for those times where the pipe does change size. Because we noted that if a fluid is flowing through a pipe and the pipe changes size, one thing that must remain the same is the amount of fluid that flows per second, or the volume flow rate. If you have a gallon of water flowing through a pipe per second, and then you constrict it, you still need a gallon of water flowing per second out of the other side. So in order for that to be true, since you now have less room for the water to flow, the water has to speed up. So the speed of the water changes because you've changed the size of the pipe. And so in order to figure out how the speed changes, we have the second equation called the continuity equation. And it said A1 V1 is equal to A2 V2, where A is the area of the pipe, the cross-sectional area, how big the opening is, and V is the velocity of the fluid in that part of the pipe. And so the combination of these two equations allows us to solve all of these pipe system type problems. And I want to make a note here to be very careful when you're doing these Bernoulli problems, that you read the problem carefully and you understand what's important and what's not. There's going to be times where there's information given in the problem that is unimportant. And I know that happened on the second test, and it happens every semester I teach this material, where I may give, the speed of the fluid into a part of the pipe and the size of the pipe, and that the pipe changes and goes up to the second floor. But I don't tell you about the new size of the pipe. I don't tell you how the pipe changes size. And inevitably, I have students either try to force numbers into the continuity equation to see how the velocity would change. Or I would, of course, have students email me or ask me in class during the test and say, hey, look, it looks like I'm supposed to be given a new size, but it's not in the problem. Did you forget to give me this information? And the answer is no, I didn't. Just because I gave you the size of the pipe originally doesn't mean it has to change. If the problem doesn't say that the pipe size changes, then it doesn't change. Now, that's not to say I don't make mistakes, because obviously I do. And so I'd much rather, if you're unsure when you're reading the question and it seems like there's missing information, I'd rather you email me and say, hey, look, it looks like I should be given some more information, but it's not here. Did you forget to give it? And if it's possible I did forget something, I would send an email out to everybody to let them know, oh yeah, by the way, number 3, I forgot to give you this. Or I'll just tell you, actually, no, you don't need that information. All the information you need is in the problem. In which case, maybe the size of the pipe didn't matter because it doesn't change. So don't be afraid to email if you have a question about these things. It seems like I'm missing information or something like that, because it's possible I make a mistake. But also, don't be afraid to not use some of the information if it's not needed to do what you need to do. There could be information in the problem that is just not necessary. So just be careful when you read the questions that you understand what's needed and what's not. I'll say that. Then the next topic of fluids, past Bernoulli, was the pressure-depth relationship. Pressure-depth relationship. And this had to do with the fact that when you go into a fluid, the further down you go, the more pressure you're going to feel because there's more of that fluid pushing on you, trying to squeeze you. And so the equation that tells us how much pressure you would feel is P is equal to rho. That's the density of the fluid, because of course, what type of fluid you're in matters to how much pressure you'll feel. A thicker fluid, let's say water, is going to push on you a lot more than something like air, which is thinner. So it should depend on the density of the fluid times G, which is just 9.8, times H, which is how far down did you go. The further down, the more pressure you feel. And then once this was brought up, some other thing, concept becomes important, which is the concept of absolute pressure versus gauge pressure. Because of course it's true, the fact that we are on the Earth and the Earth has an atmosphere. The atmosphere is made of gas, and gas is a fluid, that everything on the Earth feels a pressure because it's in the atmosphere. And so sometimes it's important, but sometimes it's not important to know the fact or keep track of the fact that you already have a pressure on you. For instance, if I'm worried about filling up the air in my tire, I don't care about the atmospheric pressure pushing on the tire when it's empty. It doesn't matter to me. What I care about is how much extra pressure, how much air do I need to stick into my tire? So all I want is the gauge pressure. How much more pressure do I have to put on top of atmospheric pressure? But maybe you're a scientist designing special machines or experiments to go into satellites or different things, and the amount of pressure felt by this machine is extremely important. And so in that case, you'd want to know the total pressure felt. So you'd want to include the fact that atmospheric pressure exists. And so we have a little equation that says the absolute pressure, also called total pressure, is whatever the pressure is due to the atmosphere, the pressure you already feel just sitting here, plus the extra bit because you changed something, you dove down into water or something like that, which is called the gauge pressure. So the pressure depth relationship, that's the gauge pressure equation. Because all this does is keep track of how much extra pressure you feel as you dive down. It doesn't tell you the fact that you're already in the atmosphere. And so because of this, when you read a question that has to deal with this stuff, you have to be careful to see what is it asking for. Am I asking you for the total pressure or the absolute pressure? Then you better include atmospheric pressure. Or does it not say you want the total pressure? The rule I'm going to use for our test is assume all I want is the gauge pressure unless the question specifically asks for the total pressure or the absolute pressure. So for instance, if the question is you're a diver and you dive down under the surface of the ocean 30 meters, what pressure will you feel? Well, there I don't ask for total pressure. I just say what pressure are you going to feel? So assume I mean gauge pressure. Or I'll say a piece of equipment slips off a boat and falls down into the water 25 meters. What's the total pressure felt by this machine? Total pressure means I want the absolute pressure. Include atmospheric in your calculation. So that's the difference between gauge and absolute pressure. Then we talked about Archimedes' principle. Ooh. Archimedes' principle. This was basically a set of relationships that had to do with buoyant force, pretty much. The fact that when you place an object in a fluid, the fluid always applies some kind of force to it, usually upwards, let's say, and we call that a buoyant force. So you put some ice in water, the water applies a buoyant force to the ice, pushing it up, and thus it floats. Or you throw a rock into a pond, of course, the rock sinks, but even though it sinks, it feels lighter than it normally would because the water applies a buoyant force to it. It's just not enough to overcome gravity, and so it still sinks anyway. And so the series of relationships we had for Archimedes went like this. Firstly, you put an object in a fluid, the object's of a certain size, and so to accommodate that object, that amount of space has to be moved out of the way. And so we say the volume of the fluid displaced by an object is, of course, equal to the volume of the object itself. You put a big object in water, there's a big space you have to move out of the way to make room for the object. And so you move all that water away, and so the water level rises or something like that. And then it turns out that if you take that amount of water that was moved out of the way and you weigh it and you figure out how much that amount of water weighs, it happens to be the same as the buoyant force which is acting on the object. So the buoyant force acting on an object that's placed in some water is equal to the weight of the fluid displaced by the object. And so now we have a way of figuring out how much buoyant force an object would feel. And with that, we could say, will something sink or will it float? Because if the buoyant force is less than the weight of the object itself, then it's going to sink, of course. But if the buoyant force is equal to or greater than the weight of the object, then it's pushed upwards harder than it's pulled downwards by gravity, and so the object would float. And this was a way of figuring that out. And then the next two relationships are just kind of a way of rewriting this equation in a new way. So the first one says the buoyant force is, well, what the heck is the calculation for the weight? Well, it's density of the fluid times G times the volume of the fluid. You want to know how much that amount of water weighs? Well, take the density of water times how much water did you move, that's the volume of the water, and multiply by G. And that gives you the weight of the water displaced. So you just rewrote it by saying weight is equal to rho GV. That's it. The last one just says, hey, let's use the first relationship, the volume of the fluid is equal to the volume of the object, to rewrite it again. And so we say the buoyant force is density of the fluid times G times the volume of the object. And so there's three different ways of writing the same exact thing. Buoyant force is equal to the weight of the water displaced. And the other two just tell you how to calculate the weight of the water displaced. That's it. Now, another thing we can do once we know about buoyant force is we could say, well, if everything feels a buoyant force when it's placed into a fluid, then obviously everything is going to feel lighter than it normally does. So let's figure out what's called the apparent weight of these objects, or how heavy does something feel when it's placed into a fluid. And so the apparent weight, how heavy something feels, is of course the actual weight, the true weight of the object, if it's not in the fluid, minus how much force is opposing it, which is called the buoyant force. So the more buoyant force the object feels, the lighter the object feels. So apparent weight is the actual weight minus whatever the buoyant force is. And of course, Archimedes tells us how to calculate the buoyant force. Finally, the last little topic for fluids is what's called the percent submerged calculation. And this is a way of figuring out what could be a fairly complicated problem. You have some complex object that you put into a water or a fluid, and let's say it floats. And you'd like to know, okay, what's the density of this object? Well, if you happen to know how much of the object is actually under the water versus on top of the water, this is very easy. We say the percent submerged, that is how much of the object is underwater, is equal to the density of the object divided by the density of the fluid. So if you have a big old aircraft carrier made of a whole bunch of different materials, all sorts of stuff on top of it, like planes, chairs, beds, all sorts of stuff, and you're asked to calculate the density of that thing, that's very difficult to do. But if you take a look at it while it's sitting there in the ocean and you see, oh, 20% of the aircraft carrier is under the water, then you just say percent submerged is 20%, 0.2 is the density of the object, the thing you want, divided by the density of the water, 1,000, whatever it is, and you solve for the density of the object. The only thing you have to be careful of is, does the question tell you how much is above the water, or does it tell you how much is below the water? To use this, it's how much is submerged, so how much is below the water. So be careful when you're reading the questions that the question doesn't tell you how much is above the water. The aircraft carrier, 3/4 of the aircraft carrier is above the water. Well, you don't put 3/4 here, you put 1/4, because you want how much is below the water. And that's it for fluids. So that's the second test. These are all the topics on the second test. The last topic is on light and optics. And this is what test 3 was on. And so we're pretty familiar with that because we just had our test on it, but we'll go over it anyway. The first topic here dealt with waves. So for waves, we had several relationships, several concepts we had to know. The first is that for any wave, the velocity of that wave is equal to the frequency times the wavelength. And of course, if we're talking about light specifically, we know that the speed of light is called c, and it's 3 × 10⁸ meters per second. Okay, so it's a special number. All waves have a speed. Light has this very special one. Other ones have different speeds. A sound is 343 meters per second, for instance. A wave on a string may be 1,500 meters per second or something, or 5,000, depending on its tension. So all waves will have a velocity. Speed of light is very special. And we know there's a relationship between the 3 big characteristics: velocity, frequency, and wavelength. But there were other things. For instance, there's the period of oscillation. Period t is just 1 over the frequency. Very nice, very easy to remember. There's something called the angular frequency, omega, which is just 2 times pi times the linear frequency, f. So if you know frequency, you could get angular frequency. Then there was k, the wave number. The wave number is related to wavelength. That's 2 pi over the wavelength. You know the wavelength, wave number, very easy to calculate. Now, the reason we wanted those things is because there's another big equation we have, which is what's called the functional form of a wave. And what it says is the height of a wave at a specific place and time is given by its maximum amplitude. So how high does the wave get? The highest it can possibly get, that's A, times the sine of kx minus omega t. And so with this, we can answer questions like a wave has a speed of 500 meters per second and a wavelength of 20 centimeters. Write down the functional form of this wave. And so you'd use these different relationships to try to calculate k and omega to be able to write in all the information for this particular equation. From there, we dealt with what's called polarization. Polarization, if you remember, is defined as the direction of oscillation of the electric field. That's what it is. But what did we do with it? We said, look, if light is polarized in a certain way, and we want to send it through a set of polarizing filters. So pieces of material that will block light or let light pass depending on its polarization. And we want to know how much light will get through the system depending on what the system is. And it goes like this. It's the law of Malus, if you remember. The intensity of the light that makes it through is whatever the original intensity was times cosine squared of theta, where theta is not just a regular angle, it's actually the difference between the angle of the light originally coming in, I shouldn't say originally, the angle of the light hitting the filter and the angle of the filter itself. So for instance, if you have light that's polarized vertically, it's at 90 degrees, and that light is trying to get through a filter that's polarized at 30 degrees, then you'd say, okay, the light's currently at 90, it's trying to get through 30, 90 minus 30 is an angle of 60 degrees. 60 would be the theta I use. And then, of course, if we have multiple filters instead of just one, well, all we have to do is multiply a cosine squared theta for every single filter. And that's the general rule. Given a system of filters, you're going to have a cosine squared for each filter. Now, the one exception to this rule is the special case where you have unpolarized light. If the light starts unpolarized, then the first filter does not get a cosine squared. The first filter gives you 1/2. But then after that, everything else gets a cosine squared because now you're polarized. That's the one exception. The main rule, every filter has a cosine squared. The exception is if you start unpolarized, the first filter does not have a cosine squared, but the other ones do. The first filter would give you 1/2 instead. And so that was polarization. Then we had refraction. The bending of light due to going through different media. You know, light is incident on the surface of a pond at an angle of 30 degrees. Calculate the angle of refraction. That's a typical type of question. It says N1 sine theta 1 is N2 sine theta 2. Snell's law. You're going from air to water. The one stuff is air, the two stuff is water. N is called the index of refraction. That tells you about the speed of light in the material. These will be given on the test. So N for air is 1, for water is 1.33, and so forth. And then the thetas are the angles of the light. So theta 1 is the angle that light makes in the first medium. And then theta 2, of course, is the angle it makes in the second medium. And usually we call that one the angle of refraction. Now, along with this, kind of a special case of refraction is called the critical angle. The critical angle is a special case where specifically you're starting in a more dense medium and you're going to a less dense medium. That's the first requirement. If you happen to shine light from a more dense medium to a less dense medium at this very special angle called the critical angle, then the angle of refraction happens to be 90 degrees. That is to say, the light skims the surface. It does not leave into the second medium. And so the way we calculate the critical angle is we just use Snell's law, but we modify it just slightly in that N1 sine of theta C. So theta 1, the angle coming in, is the thing we're trying to find. What should the angle I shine my light at be such that the light skims the surface? So theta 1 becomes critical angle equals N2 sine theta 2. Well, theta 2, if I'm shining at the critical angle, what that means is theta 2 has to be 90 degrees because it's skimming the surface. So it automatically becomes 90. And then we use that to calculate the critical angle. So it's not a separate equation, even though a lot of textbooks like to show it as a separate equation. It's just Snell's law under the special case where theta 2 is 90 and theta 1 is what you want. The other case is I know theta 1 and I'm looking for angle of refraction, which is called theta 2. So don't confuse them. Critical angle, you want theta 1 and you know theta 2 has to be 90. Angle of refraction, you know theta 1 and you're looking for theta 2. And that's it. That is all of the topics. 3 major topics: light and optics, fluids, and thermodynamics. Each test we had this semester covers one of the topics. And so obviously the best way to study for this is to go back over the old tests. Take the old tests, get a blank sheet of paper out and redo them as if you're taking them for the first time and see how you do. If you could do all 3 tests with no problem, you don't have to look things up or anything, then you're going to be perfectly fine for the final exam. Because obviously, if I felt the questions important enough to put them on the tests, they're still important enough to be found on the final exam. Now, that is not to say the final exam is just going to be exactly the same questions that you found on the test, obviously. However, the types of questions will be the same. There's not going to be anything weird on the final that you didn't see either in class or on the test. Same material. Given there's about 12 to 15 questions, well, expect something like 3 or 4 questions each topic. Or maybe think about it like one of every of these subtopics or more. Now, if you want more practice than just looking at the old tests, of course, look at the practice problems that are posted on Canvas. There's plenty of practice problems from each one of these topics. Go back, look at them, try to work them yourself. If you're having trouble, the solutions are posted there. You can look at how I work them myself. And then, as is always true, if you have any issues as you're studying for the test, you're working a problem, you don't know why you're not getting the right answer, send me an email and ask me. Take a picture of your work, send it to me, and I'll take a look at it and see what I can do. But Thursday, May 5th, that's when our test is. Again, online, just like the previous test, posted in the morning, due by midnight that night, 11:59 actually. My recommendation, since it's the final exam, it's very important. Don't wait till midnight to submit it. Submit it at 9 or 10. That way, if there's a technological issue, you could send me an email. I can get it and say, okay, this person did try to submit it. They're not just messing with me and they didn't actually do it in time or whatever. And we can go from there to figure out how to get the test. Maybe send me a copy just so I have it, so I know you did submit it in time. There's no delay or anything like that. And the other big thing is, other than just emailing me while you're studying, during the test, if there's any weird thing about the test, anything you're not sure about, you think maybe there's some missing information, whatever, send me an email, because I'd rather you ask a question where there's not actually a problem, and I just say, no, there's no problem. Everything you need is there. Rather than there is a problem and you just didn't send me an email about it, and then I didn't know that I forgot to give a piece of information somewhere. So don't be shy about sending me an email during the test if there's something wrong you'd like me to take a look at. So other than that, that's all I have. Do you have any questions about the final exam? All right, well, of course, I'm going to post this to Canvas just like all the other ones, so you can take a look back at this just to see the topics and the different equations we use. But that's all I have, so I wish you luck with your exams. I'll send an email when the test is posted, and we'll go from there. So talk to you next time, I guess.
All right, have a good one.
All right,
Thank you.
appreciate it. Thank you.